So when we start looking at trig, everything's pretty much restricted to a right angle triangle. And that would be wonderful in a world where angles only went between 0 and 90, but obviously angles can keep going round and round and round, so we have to know how to deal with angles of any size. So we imagine our number plane here, and we draw in our circle. Now, traditionally we start 0 over there at the positive x-axis, and we go around anti-clockwise when we do our numbers. So 90, 180 and so on. And we label our quadrants also in an anti-clockwise direction, 1, 2, 3, 4. And there's what I call the butterfly, because everything comes back to acute angles, because it all comes back to those original right angle triangles that we drew. So we want to rewrite things in terms of acute angles. And our angles are always measured to the horizontal. And so the butterfly is actually 4 right angle triangles. So in quadrant 1, everything's fine, because as we start from 0, in quadrant 1, everything is between 0 and 90. We don't have a problem. We can just do normal trig. So once we get past 90, we're in our second quadrant now. So in the second quadrant, we call it the 180 minus theta, because again, the acute angle that we're interested in is measured to the horizontal, so it'll always be 180 minus that. To work it out, well, sine is opposite over hypotenuse. Well, opposite is the y value. In that quadrant, it's positive. The hypotenuse is a distance, so it's always positive. So hence why sine comes up as a positive ratio. Whereas cosine, the adjacent, would be the x value, which is negative, over the hypotenuse, which is positive. So cosine gives a negative value. Tan, opposite over adjacent, also gives us a negative. And that's why the different trig ratios are the sign that they are, between 90 and 180. And we can do a similar thing in the third quadrant. It will always be 180 plus the acute angle. And then when we look at that triangle, sine turns out to be negative, cos is negative, tan is positive. And in our final quadrant, 360 minus the acute angle, sine's negative, cosine's positive, tan is negative. Now, why do we need to know that? Before calculators, and we had to look up trig tables, the tables that they gave us were only in terms of acute angles. So we needed to be able to convert everything, and we needed to know, okay, well, if it's between this and this angle, I know it's positive, and so on. So if I got a question like this and I had to work out what's the sine of 260, but all I know are the acute angles, I'd say, well, 260, that's in the third quadrant, so I know sine's negative. It would be the same as the acute angle of 80 degrees. 180 plus 80 would give me 260. I could then go and look up my 80 degrees in the tables and come out, oh, right, so that's negative 0.9848. Tan 220, same deal. I go, oh, 220. Oh, it's also in the third quadrant, isn't it? So it'll be positive, but it'll be the same as tan 40. Look up the tables. There it is. Secants. That was a little bit trickier because we only had tables for sine, cos, and tan. But that's all right. Secant 105. 105 is in the second quadrant. Secant's the reciprocal of cosine. Cosine's negative, therefore secant's negative. The acute angle is 75. I'd look up cosine 75 and then find its reciprocal, 3.8637. Okay, 430, if we get an angle bigger than 360, no worries. We just keep taking off 360 till we get an angle that we can deal with. In this case, I get an acute angle straight away, so cos 70. Negative angles just means I'm going around in the opposite direction. So negative 67 would be the same as going around 293. 293, fourth quadrant, tan's negative. The acute angle is 67. What does that tell me about the tan function? Yeah, it's an odd function. Because function negative x is equal to the negative of function x. So if I have to find the coordinates of P on my unit circle there, or actually this one's 5 units in width, well, it's just basic trig again. So x on 5 cos 30, there it is, 5 cos 30. Cos 30, of course, is root 3 on 2. 5 root 3 on 2. The y value, sine 30, 5 on 2. There's my coordinates. Well, what about the boundary values? How do we deal with the boundaries? So 0, 90, 180, 270, they're not actually in a quadrant. They're the boundary between two quadrants. Well, I draw up this fictitious triangle. One angle is 0. It's a right angle triangle. Therefore, the other angle is 90 degrees. Okay? Now, the base is 1. The height must be what? 0. Because it's 0 degrees. I haven't lifted any. So it's actually sitting on top of it. And by Pythagoras, therefore, I can work out the hypotenuse, and that's 1 as well. So, sine of 0, opposite over hypotenuse, is 0. Cosine of 0, adjacent over hypotenuse, is 1. Tan of 0, opposite over adjacent, is 0. So there's my boundary values that I can start with. And then, of course, 90 degrees I could read off the same one. Tan, we get a bit of an issue, because, of course, you can't have 1 over 0. That's why the tan curve, when you draw it, you get the vertical asymptotes there at 90 degrees. So it's undefined. 180. Well, sine 180, it turns out to be 0. You could think of it like saying, well, it's on the boundary of the second quadrant. In the second quadrant, sine is positive. It would be the same as 180 minus 0. So it'll be the same as sine 0, which is 0. Cosine, you'd say, well, second quadrant, it's negative. Or you could think of it as third quadrant. Third quadrant, it's negative as well. So either way. And it would be the same as 0 as well. So you get negative 1 and so on. And 270, there we go. And, of course, then you get back around to 360, which is the same as 0. Well, these days with calculators, you can just punch it in your calculator. There's the answer anyway. All right, so let's draw up these graphs. Whenever you're drawing a trig graph, it's the boundary values that are important. So, all right, I'm going to draw the sine graph. I know it goes up to 1, down to minus 1, the basic one. And I'm going to plot every 90 degrees, although I've only labelled on the 180s. I'll go back a bit, forward a bit. And when I'm drawing a sine graph, I say to myself, well, I know it starts at 0. That sine 0 is 0. So I'll plot that in first. And then it goes up, because sine 90 is 1. And then it just alternates. It repeats that pattern in a nice fashion. So there we go. Boop, boop, boop. Up and back the other way. Now, unlike when you were, I don't know, probably even before you started to go to school, and your parents gave you a dot-to-dot book. And what did you do? You drew nice straight lines between all the dots and got really weird shapes. It's not dot-to-dot. We don't have a zigzag. We have a nice smooth curve, of course. So there it is. Y equals sine x in all its glory. All right. Domain, or real x. There's no breaks in the sine curve. Range, between minus 1 and 1. Period is something we talk about with trig curves. Period simply means how long till it repeats. Okay? How long till you're back at the same point, but travelling in the same direction. So when you look at 0 and you think, oh, hang on, it only took me 180 degrees to get back there. But the first time you were going up, the second time you're going down. It takes 360 degrees till you're going back in the same direction at that point. So 360 degrees, it is an odd function. If you rotate the curve 180 degrees, you get the same curve. So therefore, this could be useful in some of our questions. We could use the fact that the sine of negative x is the negative of sine x. Okay, let's draw a cosine. And of course, they're basically the same graph, because cosine is the complement of sine. So therefore, the cosine of x is the sine of 90 minus x. Well, that means we've shifted the curve, but it's minus x. So what would that mean? So, let's get all those points in. I start at 1. This time we go down to 0. Again, that pattern keeps going. And back the other way. And we draw in our curve. So yeah, basically same curve, just with that 90 degree shift happening there. Same curve, so the domain's the same. The range is the same. The period's the same, but this one is an even function because it would fold on top of itself. Cos of negative x is equal to the cos of x. Again, that could be useful in some problems we need to solve. All right, let's complete the set. Tan, I haven't marked in anything on the y-axis because we don't have an amplitude when we talk about tan. Its range goes all the way up and down. So 0, then we have an asymptote. And that pattern repeats. 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, 0. And then we draw it. Now when you draw a tan curve is not a cubic. Right? So you don't draw it like a cubic where it goes horizontal. It should cut through 0 at 45 degrees. Okay? That should be 45 degrees it comes through. And that pattern repeats between all the asymptotes. Whee! Look at that. Beautiful. That makes writing the domain very interesting. Domain. It's all real x, except we've got all these asymptotes. So I guess the neatest way of writing that is saying, well, except 90 degrees, and then every 180 before and after that. So I'll just say plus 180k, where k is some whole number, some integer. Range, a lot easier to write, of course, all real y. Period. This one repeats every 180 degrees, so it's a little bit different to the other ones. And it is an odd function. So tan negative x is equal to the negative tan of x. All right. Just say we did have to draw one of the reciprocal graphs. I'm not going to draw all of them. I think I'm just going to do, cosec. Cosec reciprocal of sine. So to do it, I could say, well, there's my basic curve, sine. I'm going to do the reciprocal of this graph. Now, our rules for reciprocal. Asymptotes became x-intercepts. Well, there are no asymptotes here, so I don't have to worry about that. X-intercepts became asymptotes. So everywhere there's an x-intercept with that sine curve is now an asymptote. 1, you remember, was a key point. Because if you turn, hang on, I know who we can ask this question to. If we turn 1 upside down, what do we get? Very good. So if we turn 1 upside down, so all these peaks will remain there. Those points will remain there. So where's 1, negative 1, and so on. But the other thing we said was anything below 1 goes above 1. So we end up with a whole series of these U-shapes going along. So there's our cosecant graph. The secant graph obviously would look very similar, but shifted. And cotan ends up looking like a reflection of this. Because the x-intercepts become asymptotes, the asymptotes become x-intercepts, still has to bend towards the asymptotes, but it has to stay positive and so on. So it looks like it's going the other way when you draw it. All right, enough of me talking. We shall do 4D.